Hi everybody, this is lesson 2.1, How Crowded Are We? So let's read the specific objectives for this lesson. So students will understand that population density is a ratio of the number of people per unit area. Proportionality can be used to compare population densities. Students will be able to calculate population densities, determine if two population density ratio are proportional to each other, and compare and control population via their densities. Now, some of the words might be familiar to you, some of maybe not. We do see the word ratio being used and the modulus 1. We have seen ratios in different contexts as fractions and comparing large numbers and so on. So we'll see how the ratios will be used in this class. All right, so let's read the problem situation number 1, using ratios to measure population density. Did you ever notice that during rush hour that there are more people packed in a subway car than late at night? The size of car remains the same, but the number of people in the car has changed. What has changed is the population density. The population density is used to analyze such phenomena as the spread of disease, the distribution of resources, and the planning of urban spaces. Now, the idea of population density would be what? Can you maybe describe it in your own words? What is population density? How do you perceive it? I'll give you a minute for that. Well, the population density right now in the age of coronavirus, we think, we hear about social distancing. And I think that this lesson is something that will be very relevant to today's events. So the idea of how people are spread apart, right? So right now, for example, the recommended distance that people keep from each other is 6 feet or 2 meters to maintain safe distance from one another. So this idea is what we're going to be describing in this lesson. Alrighty, so let's take a look at the mathematical definition of population density, and it is right here. I can just highlight it. So it's defined as number of people divided by the area these people take or occupy. All right, so that's a mathematical definition, and we're going to look at New York City, and we're going to look at the 5 boroughs of New York City, and here you have those numbers. You have the area, how big each borough is, and its population. Okay, by looking at this, you see that Queens is by far the largest borough of all, and Brooklyn is the largest by the population. I believe this is the data from 2014, so now the numbers are slightly higher, but still they're in the same range. So now looking at just the numbers and without doing any computations, just by looking at this idea, which do you think is going to be the most dense and which will be the least dense? Can you make a sequence of numbers? Do not do any calculations. So I'll give you a moment. Can you list the numbers from the most dense to the least dense? The density and being crowded is a similar idea. All right, so which one is the most crowded and which one is the least crowded? Alrighty, so some of you might have said that Brooklyn is the largest by population, so therefore it might be the most crowded as well, right? Because it's the largest, okay? Or you might have said, oh, Manhattan is the smallest in terms of its size, and therefore it might be crowded in terms of how many people live there for that space. Okay, so there's no right or wrong answer until we're going to try to do the calculations. And here's what we're going to do in part B. We're going to go and calculate the densities of each borough, and I'm going to ask you to put some of the answers here as the questions will pop up. Alrighty? Okay, so let's review. So look, when it comes to calculation, I'm going to do just calculation from one of those boroughs on paper, and then we're going to do the rest on Excel just so we can kind of quickly do, so it's not redundant doing the same thing. So let's look at the Bronx. and look at its density. So to calculate the density, we're going to take the number of people and we're going to divide it by the area in that order, okay? So what we get is the number of people that there are in the Bronx is 1,418,733 people divided by the area of the Bronx, which is 109 square miles. All right, so let's take a calculator and then divide. I'm going to do this on my calculator here, and you should do the same. So 733 divided by 42, we get the number 33,000. So let's write that down, 33,779. We're going to round it to the nearest person, and look at this. The units here is going to be people, and since we divide it completely, what's left is 1 square mile. What does that mean? What does it represent? How can we perceive it? Well, you know, Bronx is a large borough to the north of Manhattan, and there, if you know the map of New York City, I'm hoping. So looking at kind of describing this, if this is 1 square mile, what is a square mile? It means you have 1 mile here, you have 1 mile here. All right, 1 mile is about, I believe, is a 10 or 20 city blocks, or 20 streets, like in Manhattan, if you count it that way. So it's 20 by 20 city blocks region, right? And there, it's not that you're going to find that many people live there. No, it's not what that means. It means if you take all people in the Bronx, which is 1.4 million, and you spread them equally to the space that's available, then you will find 33,779 people in one dot square piece of area. So why would you want to do something like this? Well, that allows you to compare places in terms of density and in terms of crowdness. So now let's take a look at the other boroughs. So I'm going to pull up Excel. I already prepared the numbers right here. Okay, so I'm going to ask Excel. Let me zoom in for you a little bit here. All right, so we're going to go ahead and we're going to just write down the formula to do this computation. Okay, so we're going to do equal. One moment. Here it is. I was looking for the equal sign. So it's right here. So it's equal. And then we're going to take this population, all right, and we're going to divide it by this population. Let me just use, I'm using a virtual keyboard. So let me use a ratio symbol. Here we go. And we're going to divide it by the B3. B2 divided by B3. B3 divided by B2. I'm sorry. Here we go. All right. So you see, careful with the order. So you're taking the population and divided by the area, not other way around. Okay, so I'm going to drag it across. Let me see if it could do that. Oops, it's drawing there. One moment. All right, here we go. So once again, what I did here is that I divided each population divided by the area. Okay, and then looking at those numbers, now you could see that Manhattan is so much larger than all the other ones. It's twice, if you compare Brooklyn and Manhattan, Manhattan is about twice as large in terms of the density than Brooklyn. And it kind of makes sense. We know when it comes to Manhattan that it is smaller than all the other places, but the population is pretty, it's not small. The people who live in Manhattan, still 1.6 million. It's a pretty large number. All right, so if we rank them, so Manhattan would be number 1, Brooklyn will be number 2, Bronx is number 3, and Queens, even though it has a very similar population to Brooklyn, making the 4th spot. Now, Staten Island is pretty large. It's bigger than the Bronx in terms of its size, but its population is really, really small. So this is going to be the least dense borough in New York City. Okay, so that would be the list. Okay, so let's move on. It says compare the most densely populated borough in New York to the least densely populated borough using a ratio. So this is the review of the previous modules doing the ratios. So you're going to do the most to the least dense, right? And looking at the numbers, all right, let's pull up the Excel. So the most was Manhattan, so 70,703 people per square mile. These are the units. I rounded to the nearest person. And the least dense is Staten Island, which is 8,149. 8,149 people per square mile. Those are the same units. Let me double check that I got the number right. 8,149. And then we're going to go ahead and we're going to divide this on a calculator. And then we'll see what we get. So 70,703 divided by 8,149. So that's about, let's round it to maybe two places. 6, 8. And then do you remember what words we use when we get the comparison? Well, let's write that in a sentence. I'll give you a moment. All right, let's review. So we say that Manhattan is 8.68 times as dense as Staten Island. So the word times is used. So it's 8.68 times. Or you can say the density of Manhattan is 8.68 times the density of Staten Island. Okay, so that's how many times it's crowded, more crowded than Staten Island. Alrighty? Okay, let's look at the other application of this. So that's a second problem situation. All right, so let's check it out. We got the making comparison with the population density. So we got the Dominican Republic. It has a population of about 10.1 million people, and its space is 19,000 square miles. Somalia, a country in East Africa, has almost the same population as Dominican Republic, so also about 10 million, but this population occupies 246,000 square miles. Someone tells you that Somalia is denser than Dominican Republic. Using your estimation skills, do you think that this is correct? Why or why not? So estimate it. You don't have to do the exact calculation, but just what do you think? I'll give you a minute to write whether that statement is true. All right, so let's review. Now let's looking at the Somalia. So they have the same population. How do we define density? It's the population divided by the area, how much space they occupy, right? So they have this about the same population, but Somalia is so much bigger. It's so much bigger than Dominican Republic in terms of its space. So is it going to be more crowded or less crowded? All right. So Somalia is going to be less crowded. Okay, so it cannot be denser. It's definitely less dense because it has a smaller, it has a larger area. So it's less people per square mile. You can go ahead and you can calculate Somalia density. So it would be, what is it? About 10 million. Let's use the same number, people, million. So we got to write that using standard form. So 10,100,000, and you divide it by 246,000. So this is the people per square mile. So if you divide that, you're going to get, let's see, 10,100 divided by 246, which is about 41. So you have 41 people Notice those numbers are much smaller when you talk about boroughs, and the reason is because country is, significantly larger in space than when you just look at the city. All right, so you always have to think about, what are we comparing? Are we comparing cities? Are we comparing states? Are we comparing countries? So these are we comparing countries. And before I compute Dominican Republic, one thing you can note is that Somalia divided by, Dominican Republic will have, in terms of its space, how many times larger than Dominican Republic? Well, if you divide them, divided by 19, you get a fraction of about 13, 12.9. So that means the Somalia is 13 times as large as Dominican Republic. That makes Somalia 13 times what? More dense or less dense than DR? Less dense, because it's bigger. All right? And now, to just double check that, if we look at the Dominican Republic, its population is about the same, so we're going to use the same figure, and we're going to divide it by the space that's much smaller, and you're going to see it yourself that the Somalia is bigger. All right, so we're going to divide 10,100,000 by 19,000, and you're going to get 531.6, if I round it. There's people per square mile. So you see how Somalia is 13 times larger, but it's 13 times smaller than, in terms of density, than DR. DR is 13 times more dense. Dominican Republic is 13 times density as the Somalia. So that's one of the things that you can note right here. The other thing is we're looking at Slovakia in Eastern Europe is almost exactly the same size as the Dominican Republic. So Slovakia and Dominican Republic are about the same in its size. And population, but the population is about 5,500,000. Using estimation, compare in percent how dense Slovakia is compared to Dominican Republic. So let's break this down. So we got Slovakia. All right. So we got, it has a population of 5,500,000 people. And its space is the same as Dominican Republic. What's the Dominican Republic space? 19,000 square miles. All right, looking at Dominican Republic, we wrote it earlier. It's right here. I don't have to copy it, right? It's right there. So this is DR. This is Slovakia, right here. So they have the same. They have the same area, about, right? The same area, but which one is going to be more dense? What do you think? Will Dominican Republic be more dense, or Slovakia will be more dense? All right, let's review. Dominican Republic is going to be more dense because it has more people and about the same space. Okay, and how many? How much more? Well, look at the numbers. If you look at the 10 million and the 5 million, it's about twice as dense, twice as populated. Therefore, it has to be twice as dense. And if we divide it, just to double check, 5,500,000. I'm gonna get rid of those zeros to make the division quicker. Divided by 19, it's 289.5. It says how dense Slovakia compared to DR as a percent. So this, if you compare this, 289 divided by 289.5 divided by 531.6 as a percent, all right, divide by 531.6 will be about 54%, about. So how do you write it in a sentence? Slovakia is 55% as dense as Dominican Republic. So you understand, when it comes to comparing densities, the larger the country is, all right, the larger it is, the more dense it becomes. And also, the smaller the area it has, then also it's going to be more dense. So when you look at this, let's say you have a population divided by the density, population divided by the area. This is definition of density, right? The bigger this, the amount of people, so the larger the population, the larger the density. The smaller the area, larger the density. So that's the idea. If you have a space area and it's very crowded, that means you have a lot of people and a small space. So look at that question number 3, the last one in this problem situation. We have City Island. It's in the Bronx. It's approximately 0.4 square miles in size and has a population of approximately 4,000 people. It's asking us, what's the population density of City Island? Be sure to include the correct units. Well, we just go again with the definition of the density. We're going to take 4,000 people and divide it by 0.4 square miles. And in this case, notice that the area space of City Island is small. It's less than a mile. So if you take 4,000 divided by 0.4, you get a result of 10,000 people per 1 square mile. People per 1 square mile. I want to ask you, does that answer make sense? I'll give you a moment to write an answer. All right, let's review. Well, you might have said, well, it doesn't really make sense because how can it be 10,000 per 1 square mile when it only has 0.4 square miles of space? It's what? Right? You have 10,000 people in 1 square mile, but this place has only 4,000 people. Well, you see, when you're dividing this, what you get is not really telling you how many people are there. What it's telling us is how dense the place is. You're basically bringing everything to one unit, and that unit is 1 square unit of space. Now, when you do this, it allows you to compare how crowded different places are. So when we get an answer of 10,000 people per square mile, if you have a place that has more than 1 square mile, then we can understand how densely populated a City Island, having 4,000 people in there. Well, it makes sense, because if there are 10,000 people in 1 square mile, and let's say the space is only half square mile, then you expect to have only half as many people, 5,000. So it does make sense, and you should be comfortable whether you're dividing by a decimal or whatever the number is. Go with the definition, number of people divided by the area. That's the sort of the concept in this lesson. Density is people divided by the area and include units, and we get how many people are there in 1 square mile of space. Alrighty, let's move on. So now we have, we talked about the City Island density, and now let's look at the problem situation number 3. Suppose that 50 years from now, global warming has melted Greenland's glaciers and raised the sea level so that City Island shrinks to half of its former size. However, the same number of people still live there. Before doing any calculation, decide if you think the population density of City Island will increase, decrease, or stay the same after the effects of global warming, and explain your answer. So let me give you a minute to think about it. Alright, let's review. So what happened here? City Island would lose half of its land, so it's going to become smaller. When we talk about density, density equals to the number of people divided by the area. Okay, so your area got smaller, so that means the people will be more crowded, right? They're going to be more crowded, closer to each other, so the density will go up. Does that make sense? If you have less area for people to be, then the density has to increase. Alrighty, next question, asking us to calculate explicitly the population density of City Island after the effects of global warming. So now let's go ahead and actually do the calculation. So the density will become, so we assume the number of people stays the same. Remember it had how many? 4,000 people. But now the island is only going to have half of its former size. Okay, so it's going to be 4,000 divided by 0.2 square miles, half of its size. And when we do the division, we get 20,000 people per one, let me move it up for you, per 1 square mile of space. Okay, again, it does not mean that's how many people they're going to all of a sudden have on City Island. It just says that the density is going to become more crowded, and if you use the space, it's only 0.2, it's going to still have 4,000 people, but they're going to be closer together. So that number indicates the measure of crowdedness. The bigger the number, the more dense it is, the more crowded it is. Question number 2 related to this as well. Suppose a waterproof high-rise building is constructed in the middle of the island and everyone abandons their apartments and moves to the building, to that building. What will happen to the population density of this entire island? Alright, will it increase, decrease, or stay the same? Let me give you a moment to answer that question. Alrighty, now in this question, nowhere it says that the island itself is losing its land. It still has whatever square mileage it has, let's say 0.2 square miles. So in other words, it's still the same area, so density will still be the same. It's going to be the same calculation. The fact that they all decided to go to that one building doesn't change the density overall. Whenever we compute the density, we're assuming that we're spreading everyone apart equally to get an idea of crowdedness as a whole space. Now, will the density of the building be crowded? Absolutely, right? Anytime you think about buildings of mass learning or whatever, where people live, those buildings are more crowded than, the land itself, the streets, right? It makes sense. For example, a school, you can have, like at BMCC, we have 20,000 students attending it. Well, at any given time, there will be, a certain amount. Now this semester it might be a little lower than the regular semester, but it's still, when you put many people in space, then it becomes crowded. So density is high for that building, but not for the entire place. You understand? Place, I mean like a city or town or state. Okay? Alright, we got one last set of questions. Okay, so problem situation number 4. It says, according to New York State Department of Health, of Emergency Medical Services, each classroom should have 17 to 22 square feet per student. This number was pre-COVID, right? So that now each student requires more space. Okay, if you think about it, if we talk about 6 feet of social distancing right now, right? So you got 6 here and you have 6 here. So 6 times 6 gives you 36 square feet. That's the recommendation in general. To have people social distance, you want to have 36 square feet of space in between them. You see, you're creating a square. 6 times 6, we're talking about the area. You understand? So, but, you probably also heard in school that if you can keep 3 by 3, then it's somewhat safer, but, that's would make it 9 square feet. But pre-COVID, that number ranged between 17 to 22. So the minimum space is 17 and the maximum space is 22, but it can be higher. I mean, you actually don't really, you wouldn't put the limit, the more space the better, right? So, but the minimum space that a student should have is 17. So that's pre-COVID, right? So, based on this information, what should be the size of a classroom of 25 students? So let's try to understand what it means. If we need 17 square feet per one student, is this a measure of density? Yes or no? It's not really. It's a reciprocal of it, because remember, the density is measured as people divided by the area, not other way around. So it's kind of also density, but it's flipped over. Now, can we use this measure to find out how much size should a class of 25 students have? Well, if one student takes 17 square feet, then how much would 25 students take? What would you do? Let me give you a moment. Yes, you're going to multiply it by 25. Alright, we'll talk about this more as the semester progresses, but we brought this question here so you can understand what the density is about, and kind of like how it connects with the idea of people and space. So that's why we brought this question up right here. So that would mean that we need at least 425 square feet of space. That's for 25, so the room has to have that size at least to accommodate 25 students. That will meet that regulation. Right now, if you use 22 square feet of space as being the higher space for each student, then you're going to need a bigger room. So 22 times 25, so it's 550 square feet. And if you use the COVID, let's say, requirement to be 6 feet social distance, then you're going to have 36 square feet multiplied by 25, and 36 times 25, that's a big room. This is like the size of the a one-bedroom apartment, so it's 900 square feet. So now you can understand, you see, the more space you need per person, right? That means the low density it is. That means the more space you need for the group of people. Alright, so these are some math that actually use in everyday life, especially in our new reality. And the last question, does a classroom of 650 square feet containing 23 students comply with the standards set by the New York State Department of Health? Well, we can actually go ahead and calculate. So if you have 650 square feet, 23 students in it, can you calculate area per student? Not the density, but the area per student. This is a reciprocal of the density. Well, let's do this. Let me give you a moment. So calculate the area per student and then see if it fits the regulation, even the COVID regulations. Alright, let's see. 650 divided by 23. So 650 divided by 23, that gives us 28.3 square feet per student, per one student. So 28 is outside, well, it's more than 22, right? It's more than 22. So that means that they're giving even more space than's required. So that's even better. Okay, it says 17 to 22, that's the kind of a range, but if it's more the better. So yes, it definitely satisfies the requirements set in the question. Now schools, just let me retract it, do not have a requirement to have a 6 by 6 feet area per student at this moment. It's recommended number, so that number, for example, does not fit that regulation because it's under 36, but it is above what it was, it required by the New York State Department of Health pre-COVID. Alright, so right now you can check it out. I don't know the details, we can look it up, but for the matter at hand, the question right here, 28.3 does indeed satisfy and comply with the New York State Department of Health requirement written in this question. Alrighty, and on that, we're going to end the lesson.